spring breaks. Now, unfortunately, it's not 2 separate weeks off, but anyhow, we're having a couple of spring breaks. So here's what's going to happen. If you're in Group A, remember, Group A is the red, okay? In Group 1, sorry, is red, and Group 2 is the blue. So if I go up here, this is the coming week, February 8th through the 12th. So if you are in Group 1, irrespective of whichever section you're in, you are going to do experiment 3.7, okay? And then this next Friday we'll have no lab lecture. However, in week 5, so this is if you're in Group 2, you are also going to do experiment 3.7, but that's only going to be the Tuesday section. So that's section 010 and 020. And the reason why sections 0.030 and 040 won't be doing the experiment during week 5 is because the first spring break is from February 17th to the 19th. So for those people, I've put it all the way down here. So you're going to have a ways to go. So it's a good thing, I think, that I'm going to record this lecture and post it to my YouTube channel. And that way you'll be able to peruse it before coming to the lab, because I won't expect that you'll remember every detail that you learned about the experiment. Anyhow, so there you go. So that's what we're doing over the next 2 weeks. Again, the only people that there's really a caveat for are the people who are in Group 2, Thursday lab. So that would be Miss Herring and me. And I know Miss Herring has 2 sections, but her Thursday section and my section, we will do this experiment during week 9. Okay. And again, that's just on account of the first spring break. And you see there's a second spring break down here, and we'll worry about that when we get closer to it. Okay. Another thing I wanted to address was.
I have a question real quick.
Go for it.
So for that spring break, are we going to have lab lecture on that Friday? Since it says it's technique C.
I'll have to see about that. Probably not. I might have to bump it up. Yep, that's a good point. I'll make a note of that, and yeah, I'll make a note about that.
Thank you.
Yep. Thanks for pointing that out. Okay, good. Well, let's take a look at Canvas just for a second. This is what you see when you log into Canvas. I'm in student view right now, and you see that we have our home, our announcements, and you can see that I posted some announcements on February 1st. And the safety quiz, everybody completed that. Our syllabus and schedule are here. Information about lab notebooks. We went over that in the first lab lecture. We went over that in detail. Then we have the UCCS list of chemicals, which you're going to need for your lab skills worksheet. We went over that with you in the lab. Then next you see the sapling assignment. So if you click on the first part of that module, it gives you all of the information about sapling. And again, I went over this during the first lab lecture, but it talks about the cost of sapling, which is $36 for the semester, and how to sign up, how to get technical support with sapling. Now, when you want to access sapling, and I have to leave student view in order for me to do this. So now I'm in instructor view. So yours doesn't look exactly like this, but if you go down and you click where it says Chem 3102, Sapling Spring 21, that will open up this window. Then you click on the load Chem 3102 Sapling Spring 21 in a new window, open that up, and it takes you to sapling. There we go. And you can see that your first assignment is due on February 11th. So that's the one that covers the content that we did in week 2 and 3. So the lab skills worksheet. And in there's just some, kind of a continuation of the lab skills worksheet, if you will. But just a reminder, it's due on February 11th, and I will not accept any excuses for it being late because it's been open for a very long time. It's been open since the first day of class. All right. Something else I want to point out, and this is for the people who, maybe haven't taken the time to look around our class's Canvas page. If you scroll down, you'll see week 4-5, that's TLC. And there's only 2 files on there. I've got the PowerPoint slides that we're going to go over today. And I also have the data sheet. So you can download the data sheet. I put it in a docx form. So if you want to type on it, feel free to do that. If you want to print it out and fill it in by hand and then scan that, that's fine as well. Just make sure that everything is legible in there. Okay, so all the information for the coming weeks, the next 2 weeks, week 4 and 5, are found in that module. All right. Well, let's get to talking about the experiment. Now, where is it here? There we go. All right. And before we do that, I'll just switch back here and ask my students, are there any other questions before we really get into it here and talk about the theory of thin layer chromatography?
For section 030 and 040, how does this divide change up due dates for the pre-lab?
Well, the pre-labs, we don't collect pre-labs, okay?
Okay.
On account of the pandemic, you have to have your pre-lab completed when you step into the lab.
Okay,
so when you come into the lab on the day that you're going to do a lab, no matter what lab it is, your lab instructor is going to check your notebook. So I just walk around the room and I do a spot check of all my students to be sure that my students have prepared before coming to the lab. So that is how we check your pre-labs. We don't collect them ahead of time and grade them separately. It's too problematic during a pandemic. And so, again, we do a spot check of your pre-labs to be sure they're completed. And then you're going to hand that in with your completed lab report. And of course, it's not handed in, it's submitted electronically. But does that answer your question?
Yeah, so we'll just wait until week 9 to present all that information when we show up.
Absolutely.
All right, sweet.
Absolutely. But for those two sections, like I said, and this is just, it's not, I don't want to use the word warning, but this is more of a, kind of an FYI. I mean, it's a long time from now, right? That's a chunk of time from now. So for those students who are in that section, I would recommend watching this video maybe on YouTube at two times the speed, maybe just quickly go over it again to jog your memory. It's something we were, my students and I were discussing in the lab yesterday, section 040. We were talking about just doing lab reports, and the students and I were saying, well, if you have 2 weeks, so if you have your mic on, if you could turn it off, that'd be great. There we go. Yeah, what was I saying? We were talking about, labs and how you have 2 weeks in between. Now, the reason we ask you to submit your labs exactly 1 week after you've completed it is because, son of a gun, is because if you wait, it's too much of a gap. If you were to start to write up a lab report, you say 12 weeks after or something, that's too long. It's too much time in between. So you want to get that done as soon as possible. All right. Well, hopefully I won't get any more interruptions from the, what are they called? Robocalls or something? I don't know. Anyhow, let's get into it and talk about TLC, not the band, not Left Eye Lopez, and what's the other one? I don't know. Anyway, let's get into what we came here for, and just can everybody see my slide here that says experiment 3.7a exercise K1?
Yes.
All right. Well, let's get going here. So the title of this lab is experiment 3.7a, which is also associated with exercise K1, which covers TLC. Anyhow, TLC is thin layer chromatography, and you're just going to hear me refer to it by its acronym, and most organic chemists will use that all the time. They'll talk about TLC. And what we're going to really be doing is TLC, so thin layer chromatography, on 3 analgesics, which is just another word for a pain reliever, and caffeine, which is a pain reliever of sorts, I guess, when you wake up in the morning. But anyhow, and here we go. Let's take a look at it. A little bit of the history, and I don't consider myself a historian with respect to chromatography, but chromatography, I guess, in some way means color writing. If you dissect the word itself, it says it's a general term for a family of lab techniques used for the separation of mixtures. So not only is thin layer chromatography what we are physically going to be doing in the lab used to separate mixtures, there are other lab techniques that involve chromatography as well. You might have heard of column chromatography, especially if you spent some time in our lab text, or gas chromatography. But anyhow, high pressure liquid chromatography. Anyhow, there are many different types of chromatography. However, they all are used for the separation of mixtures. And again, it comes from the 2 Greek words, chroma and graphene. Again, I'm never going to ask you about that. And it was invented a long time ago. Now, chromatography involves, and I'm going to use these terms quite a bit, mobile phase and stationary phase. It involves passing a mixture, something that's dissolved, in a mobile phase through what's called a stationary phase. And if you're unsure what those things are, Don't worry, we'll cover that today. Next, it says the analytes in the mixture are partitioned differently between the stationary and the mobile phases, which cause the separation. This really is, the answer to what TLC is, what we're going to be doing. If you're wondering what an analyte is, an analyte just refers to the organic compounds that we're going to be separating. The aspirin, the acetaminophen, the phenacetin, the caffeine, okay? So we have these 4 analytes, which again are organic molecules, and they're going to be partitioned. What does partition mean? It basically means they're going to be separated, right? They're going to be separated differently between the stationary phase, which is the TLC plate, and I'll discuss what that is, and the mobile phase, which is a solvent, just an organic solvent, and we'll discuss that as well. And if you're like, I'm not really sure what you mean here, Mr. Dion, I don't follow you 100%. Well, look, let's just stay on this point for a second more. The whole purpose of what we're doing is just to separate some organic compounds, right? To be able to differentiate between them somehow. And the way that we're differentiating between them is the way that they're going to separate on a stationary phase. And the way that we're going to separate them is by using the mobile phase. Anyhow, again, many types of chromatography out there, high performance liquid chromatography. So that's what we call HPLC. And there's a whole holy host of different types of chromatography that we're not going to worry about in this class. Anyhow, so here's the theory of what a TLC plate is. And you're going to hear me refer to a TLC plate. And don't worry, I stuck a picture of a TLC plate in these slides so you won't, show up and be like, well, it doesn't just look like this. I have some pictures in here. Anyhow, a TLC plate, the ones that we use are nothing more than a piece of aluminum, so aluminum foil, a thick aluminum foil, and on the aluminum foil, there is a gel. It's called silica gel, and the silica gel is made up of silicon dioxide, the formula of which is shown here. Now, when I heard the word gel for the first time, I thought of something like hair gel, or something like that. But the silica gel that is put on a TLC plate, before the plate is manufactured, it actually does have the consistency of a gel. It is a solid that is suspended in a liquid, and then they stir it around, and they actually dip the plate, and they put the plate in the gel, and then they pull it out. Anyhow, and then they dry it out. So you're left over with the silicon dioxide dried on the aluminum foil. So again, it's not a gel like a hair gel or something like that. It's actually a solid. It looks like just a regular white solid that is stuck onto the aluminum plate. So again, silica gel, it's a very common, inexpensive stationary phase. And what do you know, if you look at the TLC plate, and this would be a side view. So if you were to take your eyeball and look on the side of a TLC plate, and it's not very thick, so this is something that's very, very thin. But if we expand it, okay, what we see is we have the surface of the plate. So this would be the alumina. No, sorry. This would be the alumina, I guess, would be over here. And then the silicon dioxide is on top of that. Okay, so what do we see on the surface? We have all these exposed hydroxyls or OH units that give the silica gel a relatively polar surface, right? You guys know about hydrogen bonding. In order for you to completely understand the theory of TLC, you have to master, and this is something you should have done already, you need to understand intermolecular forces like London forces, okay? You need to understand dipole forces, okay? So dipole forces. You need to understand hydrogen bonding. And if you're thinking, well, Mr. Dion, in general chemistry, we discussed ion dipole forces and other forces. You need to know those too, but I'd say these are where you want to start, with London forces, dipole forces, and hydrogen bonding. Anyhow, here's our TLC plate. The kind of TLC plate that you're going to get in the lab is going to be a 5 by 10 centimeter plate. I'm going to give one to everybody. You're going to need a minimum of 2 to do this experiment. And the layer of silica gel, so this layer here is only 250 microns thick. So it's not very thick, okay? And there's something else in that gel. Now, it's not shown here, but it's also impregnated with a fluorescent indicator. And if you're wondering, what's the purpose of this? Is this, what's that for? What would I need a fluorescent indicator? I'll explain that in a few minutes, okay? So I'll cover that in detail. So here's what a TLC plate looks like. These are just pictures that I took off of Google Images. So the TLC plate that you're literally going to be handed in the lab will probably look around this shape, right? It's going to be about 5 centimeters by 10 centimeters. But you can see that that plate was probably cut from a much larger plate. You can literally cut these with a pair of scissors, okay? And you can cut the TLC plate as large or as small as you want. It's just that, you know, running a university lab, we found that the 5 by 10 format works rather well. Now, the reason I put this picture in here is because the backing on this TLC plate, the one that you're going to use, is an aluminum backing. However, the backing on this TLC plate, it's not easy to tell from a picture, especially if you've never worked with TLC plates before. But this one actually has a glass backing on it. And the first time I ever did TLC in my life, which was probably in 1994 or something like that, the way we did it is we took 2 glass plates and stuck them together, and then we dipped them in silica gel and let them dry. Now I can promise you that using an actual store-bought, if you will, TLC plate is much better than making your own TLC plates. But just so you're aware, you can have TLC plates on aluminum backing or a glass backing if you look around or whatever, buy different ones. Anyhow, so let's go back to that silicon dioxide, right? That stationary phase. And if you're wondering, what are you talking about stationary phase? I'm going to repeat myself a lot here. This is what I'm talking about. The stationary phase, we said it was polar, didn't we? Okay, let's go back here. The effect of that polar stationary phase. Think about it. If the TLC plate itself, the surface of the plate, this white powder, okay, this white, that's the stationary phase. That's the stationary phase. If that is polar, right, if that surface is polar, wouldn't it make sense that if you put a polar analyte, a polar molecule on it, it's going to be held more tightly than something that's non-polar? Of course. Right? If you have something that's polar, it's going to have a stronger interaction with that polar surface. Let's say you had a polar molecule that had hydrogen bonding, right? A hydrogen bond is going to interact more strongly with the hydroxyls on the silica than something that's non-polar. If you have a completely non-polar molecule, say a hydrocarbon, okay? So you try to put benzene or toluene, some kind of hydrocarbon, okay? That's non-polar. It's not going to interact nearly as strongly, or it's not going to adhere to that polar stationary phase nearly as much as a polar compound would. So my question to you is, would a polar or non-polar analyte travel faster up the TLC plate? Now, before you answer, let's think about how a TLC plate works. We have our TLC plate. Now, this is just my artist rendition. You're going to start by putting your analytes on the bottom of the plate. And by virtue of capillary action, the solvent and the analytes are going to travel up the plate. Okay, so they're going to go up. They're not going to go in a down direction. If you're doing column chromatography, yes, the analytes will go down. You use gravity in your favor. But here we're using capillary action. So again, if the surface of the TLC is polar, can you tell me which one would travel up the plate faster, a polar analyte or a non-polar analyte? And it's not a trick question. Could anybody answer that? Or just even give me a guess?
Polar. I want to say polar.
Okay, I got some interesting answers here. So let's think about it. Okay, let me try to explain it to you again. So the answer is non-polar, and let me explain why. If we have a polar surface, right, the surface of the TLC is polar. If you start with an analyte that is polar, right, it's going to want to travel up, yes, but it's going to stick, right? And I don't know how to represent that with my pencil, my Apple Pencil, but it's going to adhere to the surface of that plate. Does that make sense? Right? Because if it's polar, it's going to want to stick, right? It's going to have a tighter or a stronger intermolecular force holding it to the polar surface. If I have something that's non-polar, right, it's going to be like, meh, it's not going to interact with the polar surface. And so it's going to travel up faster. It might be counterintuitive, but I promise you that if you really sit down and think about it and study it, it will make sense to you. Okay, I promise it will if you take the time to really think about it. Well, let's talk about the solvent polarity. Because as I told you on this slide here, we're not just taking a TLC plate and putting it in the air and expecting our analytes to travel anywhere. The reason they travel is because you put the TLC plate in some kind of vessel, which we call a TLC chamber, and there's some kind of solvent. So your TLC plate is actually sitting in liquid, okay? And if you're like, what, do I cover the whole thing in liquid? No, 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 no. I said it's sitting in liquid, just a little bit, okay? And the liquid is gonna, again, travel up the plate by capillary action. So let's think about the solvents. It says here that a polar solvent is going to compete better with the polar TLC plate surface, right? The silica surface. So all the analytes, even the non-polar analytes, are going to have higher rates of elution. We have a fancy word for that rate of elution. We call it an RF, which means a retention factor. I'll talk more about that in a little bit. But what's the crux of what's being said here? Let's see if we can dissect this, because it seems like we're kind of split on, you know, in the class between the whole polar, non-polar, what's going to go faster. Listen to what it says here. A polar solvent. So if I put my TLC plate, okay, if I take my TLC plate, I've got my analytes. If I put it in a polar solvent, okay, here's my solvent. Well, the polar solvent is going to interact better with the silica, the stationary phase on my TLC plate, than a non-polar solvent would, isn't it? So let's unpack this again. Second time. It says polar solvents are going to compete better with the polar plate surface. So all the analytes, even the non-polar analytes, are going to have higher rates of elution. Right? Okay. We say that polar solvents have a greater eluting power than non-polar solvents. All right. Let's move on from there. So the 5 steps in TLC analysis. I'll give you all a heads up that in the sapling assignment for this lab, they dissect the steps in the TLC analysis into 7 steps, I think. But it's pretty much this with a couple of steps thrown in there. In one of the steps talks about visualizing the spots using a stain. And that's something that we don't do in our class, but I will talk to you about it. So it won't be some kind of foreign concept, something you've never seen before. Anyhow, here are the 5 steps. And, you know, if I was to ask you, let's say you worked at Dunkin' Donuts. If I said, how many steps are there in making a cup of coffee? You know, you could say, step 1, go over to the coffee maker, put the coffee in it. You know, step 2, sell it to client. Well, that's one way you could analyze it. 2-step process, get the coffee and then sell it. But you could also say, you know, step 1, turn around. Step 2, walk to the back counter. Step 3, grab the coffee cup. Step 4, step over to the coffee maker. Step 6, you know, step 5, press the button, you know, whatever. So I've heard it said one time that somebody broke down how many steps it takes to make a cup of coffee at Dunkin' Donuts into like 70 steps or something like that. So the 5 steps, this is just, you know, if we look at these 5 steps, these are the order in which they would occur. Anyhow, so step 1, prepare the developing chamber. Now, developing chamber sounds like a really intense, you know, title, but the developing chamber is nothing more than a beaker. Okay, it's just a 400 milliliter beaker. You've got one in your drawer. So just a 400 milliliter beaker, and on top of the beaker, you're going to put a piece of foil. So you're going to have a piece of aluminum foil to cover the top, and that's just so the vapors don't escape. And you're also going to put something that we call, well, you're going to put a filter paper in there. Sometimes you might hear it called a wick if you peruse the internet at all. Anyhow, I'll explain what that is. And the reason you prepare the developing chamber with a cover on it and with a wick is so that the entire chamber, your entire beaker, just gets saturated with saturated with solvent vapors. Next, you apply the analytes. And again, analytes is just a tsatsi word for a small amount of an organic compound. So the 4 organic compounds that we're interested in are the 3 analgesics and caffeine, and we'll talk about those more. It says here you use a spotter. A spotter is used to spot the solution of each analyte. So the solution of the analytes, those will be made for you ahead of time, and we have them like in a little screw cap vial. And all you're going to do is take a spotter. Now, if you're wondering what the heck is a spotter, I don't know what that is. A spotter is nothing more than a really thin glass tube. So thin. Now this is way bigger. I mean, I'm looking at my iPad, so I don't know what scale you're looking on. But the spotter is nothing more than a little glass tube, but it's so small that when you put it in to the liquid, so here's your liquid, the capillary action, right? And you would have discussed capillary action in General Chemistry 1 is going to pull the liquid up into the capillary tube or the spotter, okay? So you're going to have the liquid, and then you can take it out. You can pull it out of the liquid. I'm going to try my best to draw the capillary tube again, or the spotter, if you will. Then you're going to have your liquid in it, which we call an aliquot. That's just a small sample of your analyte dissolved in some kind of solvent, and then you're going to spot that on your TLC plate. And again, your instructor is going to show you how to do this. I will definitely show my students, and I know that Ms. Herring and Mr. Mayer will probably walk you through this and say, this is how you spot properly and things like that. You know, a picture is worth 1,000 words, and a demonstration, there's something to be said for that as well. Okay, after you've applied the analytes onto your TLC plate, you're going to develop the plate. It says this is where the separation actually occurs. Let me throw a step in here. We'll call it 2B, maybe, step 2B. Is you're going to look at the TLC plate, look at plate, TLC plate, under UV lamp. Okay, this is something that sometimes my students forget to do in organic chemistry too, but it's pretty important that you go just take a look under the UV light, because you won't be able to see the analytes with the naked eye. So it's nice to walk over to the UV light and just say, hey, are my analytes on there? And you know, just be sure that you've prepared the plate correctly before you start developing. Then you're going to visualize it under ultraviolet light. Now, if you go all the way back to the first slide, right, I bet you, and I wouldn't blame you, if you thought, hey, man, I thought you said it was color writing. You know, is there anybody who's hearing the sound of my voice who did an experiment maybe in junior high school or high school where you take a black marker and you put a spot on a paper towel and then you elute it with water? Has anybody done that? I did it in the 7th grade. And it basically separates the black ink into its colors. Okay, I'm not getting any thumbs up or anything. So maybe you've never tried that before. And you, okay, Jessica did great. So you might be wondering, like, I thought I'd be able to see some beautiful colors, maybe a red, maybe a fuchsia, maybe a taupe. No, the compounds that we're going to be eluting, these organic compounds, you cannot see them with the naked eye. However, they possess what's called a chromophore, which enables you to visualize them under an ultraviolet light. And I have a picture to help you understand what I'm talking about looking under a UV light. All right. Okay, dissected a worm. It's got nothing to do with TLC. And next, you're going to interpret the results. So you're going to look at the spots on the TLC plate under the UV light. You're going to mark them with a pencil, because when you pull the plate out, you're not going to be able to see it. It's going to go back to being invisible again. And then you're going to be able to identify the components. Now, if you're wondering, how am I going to identify the components, Mr. Dion? Don't worry, I've got you covered. Okay, let's see here. So again, a little more about that developing chamber. It's just a plain old 400 milliliter beaker. We'll probably have one on the instructor table in your lab. So if you can go look at it, study it, stand close to it, whatever you want to do. It's just a 400 milliliter beaker. You take a piece of filter paper and you're going to cut one side. Now, if you look at the filter papers that we have in the lab, they're just, you know, a circle. And all you're going to do is you're going to take a pair of scissors, okay, and you're going to cut off the bottom like that. And then you're going to put the filter paper with the bottom cut, you're going to put it in the developing chamber, the beaker. Okay, so the reason why you do that, why you put the wick or the filter paper in there, it's so that it becomes impregnated with the solvent, completely saturates the environment inside the developing chamber, so that nothing dries during the process. You want everything to be, you know, saturated with solvent. Okay, you want the solvent vapors to be evenly distributed throughout. Let me tell you something right now. From somebody, I mean, I worked 15 years in industry, and I probably worked, let's say, I don't know, how many days a year do you work? 200 days, you know, 300 days a year. So 300 times, I probably ran 25 TLC plates a day times 15 years. So I probably ran somewhere around 100,000 TLC plates in my life. And I can tell you that TLC conditions are actually not that easy to duplicate. I mean, you can usually get it pretty darn close, but they're not easy to duplicate. And that's why we're so concerned with RFs. and I'll explain that more in a second. Anyhow, next thing is you're going to pour 10 milliliters of the developing solvent, which is your mobile phase, into the beaker. If you're wondering what's solvent, we're going to talk about that. Next, you're going to cover the beaker with foil. You let it sit undisturbed for 15 minutes with nothing in it. Okay? You don't even have a TLC plate in there. Why? I'm telling you again for the last time, right? So that the entire chamber is completely saturated uniformly with the vapors of the solvent. All right, there we go. Okay, next you're going to apply the samples on the plate. So this is what your TLC plate looks like. Okay, again, this is the 5 centimeters by 10 centimeters, roughly. And your instructor will come around and just hand one out to you and be like, here you go, here's your TLC plate. So what you're going to do, the first thing you're going to do is you're going to grab a ruler. We've got plenty of rulers in the lab, and you're going to draw a starting line, okay, at the bottom of the TLC plate, about 1 centimeter from the bottom. Now, if you're wondering which end's the top and which end's the bottom, doesn't matter. Just draw a line, okay? That line, we call it the starting line, or I call it the baseline, okay? The baseline. Now, it says here it should be around 1.5 centimeters from the bottom. Then you're like, Mr. Dion, you don't agree with yourself. Down here it says 1 centimeter. Well, let me tell you something. You can't technically, now there's reason in all things, you can't draw the line too high. However, you can draw the line too low, okay? So don't get stingy with it and say, I'll make it 0.9 centimeters. I'll make it 9 millimeters. That way I'll have even more space on my plate. No, I would maybe draw it 1.5 centimeters. Now, that's just my estimation. If you want to discuss it with your instructor, what I usually do is I take a TLC plate, show my students, about this area is where I want it drawn. The reason why you want to make sure that your baseline or your starting line is high enough is because if the solvent was to cover that all your analytes would just get dissolved and go into the solvent. So that wouldn't help you at all. Okay? Anyhow, so there's our baseline. We've drawn our baseline. Notice you're going to draw it with a pencil. You never use a pen on a TLC plate, only a pencil. Then you're going to make a little X where each spot is. So I like to just take, my pencil, I'll make an X here, make an X here, make an X, and I'll even label them. I'll put ASP for aspirin, and then I'd put ACE for acetaminophen, then I'd put PHE for phenacetin, then I'd put CAFF for my caffeine. Now, I like the students in my section to put everything in the same order. Everybody in the room, I like to do everything in the same order. It just keeps it uniform throughout the class, and it makes it easier to compare TLC plates. Anyhow, again, you take your spotter, your glass capillary, transfer and spot the dissolved analytes. Again, they're prepared for you. You want to keep the spots small. So what you're going to notice is that if you just take your spotter and you just touch it to the plate, you're going to find that all the liquid is just going to, right? It's just going to go down, and you can end up with a really big spot. So what do you do before that happens? You kind of lift the spotter off of the plate, and that will prevent you from making a giant spot, which you don't want to do. All right, so apply that. Next, you develop this TLC plate. This is your chamber here. Again, this is artist rendition. You put the TLC plate in the chamber. Notice that this part down here, this is the solvent. Okay, notice that the solvent is below the baseline. And then, again, by virtue of capillary action, the solvent is going to travel up the TLC plate like that, taking the analytes with it. Come along with me on a journey, right? The less polar the analyte is, the further it's going to travel up the plate. The more polar an analyte, the more it's going to be retained, and the smaller the distance it will travel up the plate. All right. So again, capillary action. Now, next, once the solvent gets to around a centimeter from the top, and you're going to have to keep an eye on it. Never turn your back on an experiment in organic chemistry. I mean, there are situations, I suppose, where you could, but generally speaking, in our labs, no, I wouldn't do that a whole heck of a lot. Okay, so you're going to wait till the solvent is about 1 centimeter from the top. Then, and pay attention, listen to me very carefully here. Okay, you're going to pull the plate out with, your fingers with gloves on, And as soon as you pull that out, you're going to be able to see where the liquid was because it's going to be dark, right? But the solvents that we use have a high vapor pressure, so that means they're going to evaporate quickly. So as soon as you pull that out, you've got to mark this line with a pencil immediately. If you don't mark this line right here, which is called the solvent front, okay, if you don't mark the solvent front immediately upon removal from the chamber, the TLC plate is no good, okay? And you're like, well, why wouldn't it be any good? Because you won't be able to get the necessary data from it, okay? You might even be able to look at under the UV light and see separation, see resolution, see a difference in the retention of your compounds. However, you won't be able to calculate your RF, okay? And we're going to talk about that even more. Anyhow, if you're wondering, hey, Mr. Dion, how long does it take for this to happen? Is this like an hour-long thing for this TLC plate to develop? The answer is no. It says here 15 to 20 minutes, is usually what it takes. All right. Something else, and there's probably a few things that I might be forgetting here. I see that Mr. Mayer's, probably filling in some blanks. I'm not really reading it. But just one thing I want to remind you of is, we're going to be wearing our gloves at all times in the lab. Now, when you develop 100,000 TLC plates over your life, you can imagine I did a lot of TLC plates where I didn't use gloves. And one thing you always want to be sure of with a TLC plate is that you never touch it. Never touch the silica with your bare hands, okay, with your bare fingers. And the reason why is that oils from your fingers can get into the silica and they can impregnate that silica and it will actually affect the stationary phase, okay, which will usually result in a slower elution. Anyhow, so you definitely would never want to handle a TLC plate with your bare hands. Next, you visualize the results. I love this icon here, this ultraviolet, sun with the thunderbolts or lightning bolts, whatever. There. Anyhow, and I'll show you a picture, which will be worth 1,000 words. But on this TLC plate, so the person is visualizing it under a UV light, and they're looking for the spots. You can see there's a spot here, so on and so forth, right? And those spots are, kind of in the lanes where they would have spotted their samples, right? You see there's a spot here, there's a spot here, spot here, spot here, spot here, so on and so forth. Now, again, since when you pull the TLC plate out from underneath the UV light, you won't be able to see anything, you have to circle or trace the spots with a pencil while you're looking at it, okay? And don't press too hard with the pencil because the silica is a little bit delicate. Anyhow, you also want to mark the center of each spot. I don't know who came up with this alphabet, but anyhow, you also want to mark the center of the spot. And I'll explain why, but basically that'll help you get a good reproducible RF or retention factor. Okay, so let's talk about RF values. So RF stands for retention factor. And what you're going to do is for every one of those spots that you see under the ultraviolet light, you're going to circle it, and then you're going to report a retention factor, or an RF, which is what I'll use to describe it, for each one of them. One of the easiest formulas you're ever going to use in any science class. All you do is you measure the distance the spots moved. So let's say we were measuring the retention factor of this spot right here, okay? You'd measure from the middle of the spot down to the baseline. So you'd get this measurement T. Then you divide it by the distance from the baseline or the starting line all the way to the solvent front, which is Y. So T over Y, and if you're like, well, they're both going to be in centimeters or millimeters, that's right, units cancel out. So RF is a dimensionless number. Perfect. Okay? But it gives you an idea of how far the spot traveled up the plate, right? If you have a high RF, that means it's going to have gone further. That means it's going to be less polar than something that has a lower RF. And if you're thinking, well, Mr. Dion, if I'm dividing them all by the same denominator, which is going to be a greater number than the numerator, then they're all going to be a number somewhere between, 0 and 1. Absolutely. Yeah. Okay. All right. There we go. So that's an RF. So, and I'm repeating myself here. I just want to see if you're paying attention. I have a very quick question. If you compare these three spots, we'll call them, what are they? X. So this is spot X. Maybe I'll have to write it over here. we have spot X, we have spot Z, and we have spot T. Could anybody tell me which one of these is the most polar spot? And it's not a trick question.
X.
Absolutely. Yeah, X is most polar. T is the least polar, and Z is somewhere in the middle, right? It's intermediate. It's somewhere in between the two. All right, beautiful, great, wonderful. And then you're going to compare the RFs with some standard RF values. Now, if you're wondering what a standard means, it means nothing more than you're going to have some unknowns. Okay, you're going to be given an unknown sample. Everybody's going to get a unique one, so you don't get to share your answer with anybody else, but everybody's going to get an unknown, and it's going to contain 1, 2, or 3 of the, or 1, 2, or 3, 1, 2, 3, or 4 of the compounds, aspirin, acetaminophen, phenacetin, caffeine, and you have to determine which ones you've got. Maybe you've got only 2. Maybe you've just got acetaminophen and phenacetin. Maybe you've got aspirin, caffeine, and acetaminophen. Whatever, you need to determine what's in your mixture. You're like, well, how am I going to do that? Because we're going to give you a pure sample of each one of those, right? So here's a pure sample of a compound, here's a pure sample of a compound, and here's a pure sample of a compound. That's what we call a standard. And you're going to run those standards against your unknown. So could anybody tell me which one of the compounds that are standards are found in this unknown sample?
X and T.
Absolutely, right? Because the student said, well, the unknown, it's got a spot here. Well, darn it. It's got a spot here that's got the same RF as X, and it's got another spot here that has the same unknown, or has the same RF as T. So it probably contains X and T. Now, I don't want to get into a whole bunch of splitting hairs and making things more complicated for you than they need to be. But just as an aside, okay, so let's take a deep breath. You've been listening to me talk for a while, and I still have 3 more hours to go. But if you think about, I have a question for you. Let me do it this way. If I ran a TLC, okay, something that's never been made before, it wasn't a lab that was set up for you at UCCS. You were doing research, and you ran an unknown sample, and it had, let's say 3 spots in it, and you ran it against a standard. Now, this is a reaction you've never done before in your life, and you see, hey, look, I got a spot, I have a spot in my reaction that is the same as my standard. Does that necessarily mean, is that 100% proof that I have that standard compound, that known compound in that mixture? Could anybody tell me if it's a guarantee?
I would guess it means you have a compound that's as polar as your standard.
Couldn't have answered it better myself. Okay, so what the student is, he was being very kind, and he said it in a nice way, but he said, no, it's not a guarantee, is it? The student, he said, you've got some kind of compound with the same polarity. It doesn't have to be the same compound. There are many millions of organic compounds. Maybe it is the same compound, maybe no. So then you might be getting frustrated with me and being like, oh, Mr. Dion, how would I know? How would I know? Well, there's a bunch of things you could do. Okay, and I'm not really going to quiz you on this, but what could you do? You could run another TLC, maybe using a different eluent, maybe using a different solvent. You could use another method. Okay, and what we're going to see later on in this class, in a few weeks, is we're going to learn about what's called spectrometry and spectroscopy. And those are methods that you would use to really unequivocally state whether you have a molecule or not. Okay, so just something to think about. I like my students to think about what they're doing and understand what they're doing. Well, here are just some pictures that I pulled right off of Google Images. Okay, the one on the top left here. So it just kind of shows you, here's your TLC plate. You put your analyte on there. Pretend this is a 400 ml beaker. The person doesn't know what they're doing because they didn't put their foil on it. You got to put the foil on, right, Coach? Okay. Anyhow, you put the foil on the top. They also don't have a wick in there. So, but anyhow, then they elute it, right, by virtue of capillary action. And you can see that they separated, look, 2 different spots. They have the solvent front, they have the baseline, all marked. And there was 2 compounds, something that's more polar and something that's less polar. So when you look under the UV light in our lab in Centennial Hall, what you'll see is something like this. Okay, this isn't exactly what your TLC will look like, but something of this ilk. Okay, you'll have your baseline that you drew before the experiment even got started. You will have your solvent front. The solvent front is usually drawn freehand. You know, you usually don't have time to pull it out and grab a ruler before the solvent starts evaporating. So just take your hand and whoop, draw the line the best you can. The baseline, yes, you can draw that with a ruler because you get all the time in the world. You see how the person labeled these, called them 1, 2, 3, 4, 5, 6. Okay, whatever. You can label them whatever you want. And you can see that in the first lane, you can see there's 2 compounds here. In the second one, there's something here, right? So on and so forth. And you notice that it's not just cut and dried. You know that when you look at a picture like this, it looks like perfectly round circles, you know, spots. Well, this is more reality of what it might look like. Sometimes you see spots that are, you know, maybe a little more oval shaped. Then you have these ones here that are kind of streaky, right? It looks like a comet there or something. You have something down here, you know. So, you know, that's kind of something that we'll discuss maybe more in the lab. But you look at this is after a student traced out the spots under the UV light, and you see that in this TLC plate, wow, that is a giant spot. Okay, this really long one. We're going to try to avoid getting spots that look like that. We like to get sharper spots than that. I think this TLC plate looks really good. You can see the spot here and here, and you would measure the RF from the center. You can see that they didn't mark the solvent front though. Anyhow, actually, you know why you can't see it, I think. Yeah, you can barely see it there. Anyhow, and you can kind of see it here too. Anyhow, those are just some pictures. But again, what you're going to be seeing in the lab will look a lot like that. All right. That's oh, I know something else I wanted to tell you about is for my students who are disappointed that we're not making a beautiful separation of, you know, pretty colors. Well, you might be wondering, you know, besides looking at your sample under an ultraviolet light, are there other ways to visualize those spots so that I could see them without having to go over to a UV light all the time? And the answer is absolutely. Absolutely, you can. One thing that you can use is what we call an iodine chamber. So you're literally using iodine. And we're never going to use that in our class. We use it sometimes in the organic chemistry lab for chemistry majors. But another commonly used method to view the spots on a TLC are to use what are called stains. So they actually stain the compounds. And there are not Avogadro's number of stains out there, but there are several different stains. This one here is called a PA stain. It's para-anisaldehyde. I'm never going to ask you about this, but I want you to know that there's, you know, other ways to do this. There's vanillin, there's, you know, molybdate stains, there's, you know, permanganate stains. There's all kinds of different stains out there. But the idea is that what's cool about these stains is that once you become more accustomed to working with stains and you know what kind of functional groups are in your compounds, you can choose the right stains and it will stain compounds with different functional groups, different colors. Anyhow, it's kind of interesting. Yeah, there we go. All right, well, let's get back to our experiment, talk about what we are doing in the lab. I might have to speed up a little bit here. It says, we're going to observe the effects of analyte. Again, the analytes are just the organic molecules, okay? The analytes are just the molecules, okay? And solvent, polarity on order and rate of elution. And then we're going to identify the components or the molecules in a mixture of an unknown mixture. That's it, okay? So these are the 4 compounds that you're interested in. Now, if you look at your textbook, your lab manual, you might have read it all already before and said, these aren't the compounds that were in there. Okay, well, we've made a switch, you know, and Mr. Mayer, if any of you are in his lab, he could probably shed more light on why we switched from from the compounds that were in the textbook. I think it was fluorinone and some other compounds, maybe benzoic acid or something. Anyhow, they changed it over the years, and trust me, the change wasn't made to make it more difficult. It was made to make it better, to make it work even better. So here are the compounds we're interested in. Caffeine is a natural product. It can be isolated from coffee beans. And these 3 compounds here are all analgesics: aspirin, acetaminophen or Tylenol, and phenacetin. Right, so these are the 4 compounds that you're interested in this lab. So let's talk about what you got to do before you step into the lab. You're going to read the experiment. Will not take long. 5 minutes, 10 minutes tops. You're going to read technique K. You don't have to worry about the parts about resolution or column chromatography. You see, there's a part about resolution where it gives you an equation. I'm never going to ask you about the equation. You should know the definition, but don't stress about any kind of equation to do with resolution. You're going to prepare your notebook. We went over this in gross and dirty detail last lab lecture. I said you've got to put in a header right at the top of every page. Nothing new there. You've got to come up with a purpose. This is a good one. This is one that always seems to annoy my colleagues and me too, is when a purpose starts with the purpose of this experiment is. Well, let's think about it. If you start by writing purpose, semicolon, and you underline it, I think the person is going to know that anything that follows that is the purpose. So you don't have to say the purpose is, that's redundant. Anyhow, next you're going to put the table of reagents. That's going to include the aspirin, the acetaminophen, the phenacetine, the caffeine, the solvents that we're using. If you're wondering what are the solvents, we're going to talk about those in a minute. And we want you not only to include the name, the formula, structure, molecular weight, boiling point for any liquids, melting point for any solids, and the polarity. Ooh, what do you mean by that, Mr. Dion? Well, you remember in the lab skills worksheet, I asked you to, draw a compound, Lewis structure, determine molecular geometry, and whether a compound is polar or not. So you're going to use those same skills, and you're going to look at these molecules, and I want you to rank them in order of their polarity. What do you mean, Mr. Dion? I want you to rank them. Which one is the most polar? Which one is the least polar? And which ones are in the middle? Okay? So I want you to rank those analytes from 1 to 4, from 1 being the most polar, 4 being the least polar. And then I want you to rank the solvents, 1 being the most polar solvent to 3 being the least polar solvent. Mr. Dion, you didn't tell me the answer. I'm not going to tell you the answer, okay? I want you to figure that out. All right, well, let's keep moving from there. And we're going to talk about the solvents in a second, so don't stress about that. Next, you need to put a safety table, list all the compounds and solvents, cite the source, the UCCS, chemical list again. Next, you're going to do your procedures, right? You're going to get, I'll be honest with you guys, you're going to get most of your procedures from this lab lecture, okay? Make sure to read through the procedure in the lab manual as well, but most of it can be garnered from everything I've told you today, okay? In fact, I've repeated myself probably, 3 times with respect to everything, but that's not a bad thing when you're learning a subject. Remember, the procedure is written in the 2-column format. Left-hand side is for the procedure. Right-hand side is for the observation. If you're not following me, I went over this in the first lab lecture. I said your lab notebook looks something like this. You have your header at the top, right? Then you have procedures over here, and you have a line down the middle, and you have observations over there. Make sure that your procedure is detailed enough that a loved one or a friend or a well-wisher or a colleague in the lab would be able to follow it. What else? Besides the procedures that are in the lab text, make sure to incorporate the following. And this is something I mentioned earlier. Check the TLC plate under the UV light before you develop it. Okay? Make sure you can see spots before you start. Otherwise, you end up wasting a half an hour of your time, okay, which you don't want to do. Nobody wants to do that. Make sure that you leave enough space in the observation because we want you to put sketches of all your TLC plates. They don't have to be to scale. They don't have to be 5 by 10 centimeters, but just make sure they're drawn, well enough that we can see them. There we go. And here are the 3 solvents that we're going to use. Acetone, which is nail polish remover, ethyl acetate, which you could also use as a nail polish remover, and hexanes. Hexanes is a hydrocarbon. Anywho, and so those are the 3 solvents. All right, continued. Part 1. So we're going to break the whole lab down kind of into 2 major parts, okay? The first part, you're not going to work in a group, like you're not going to be next to somebody working with them, but you're going to pool your data with 2 other people in the lab. Let me explain what I mean. Okay, so in part 1, you're going to run a TLC on the known compounds. What are the known compounds? Aspirin, acetaminophen, phenacetine, and caffeine. Okay, so there's 4 known compounds. However, there are 3 solvents that we're interested in studying in this lab: acetone, ethyl acetate, and hexanes. So what we're going to do is you're going to run a TLC plate with all 4 of the analytes in acetone. Somebody next to you is going to run the same TLC plate, all 4 analytes that they're going to make. They're going to run it in ethyl acetate, and somebody else is going to do the same 4 analytes and run it in hexanes. Then what you're going to do is you're going to compare the data. You're going to compare your 3 TLC plates, and you're going to look at one student and say, hey, this didn't separate the compounds at all. This is crummy. I can't even tell what's what. you're going to look at somebody else and say, hey, this isn't that bad, not bad. There's some resolution here. There's some separation. Then you might look at another person and say, hey, hot diggity darn, this is pretty good. I think I could use this to be able to determine what components I would have in my unknown mixture. All right, so that's what you're going to do. You're going to pool your data, you're going to compile your data, and you're going to be able to choose the appropriate solvent. Okay, and what I like to do with my students is once everybody's done part one, I like to just have kind of a frank and earthy discussion with my students and just say, you know, what did we see? You know, what did we see as a group? What did you notice? And I like to hear the feedback from my students and get their thoughts before we all start proceeding with part two. Okay, so again, since you're not gonna run 3 TLC plates, you're only gonna run one with the 4 knowns. You're gonna record a sketch of your partners or your 2 other partners TLC plates. Throw them in your lab notebook and make sure to show the RF values. Okay, there we go. So here's the part where you're all by yourself. Okay, you're going to analyze an unknown. Again, Mr. Mayer or somebody who prepares the samples, I don't know who, is prepared all brand new samples this semester. Even Mr. Dion doesn't know. Miss Herring doesn't even know. Okay, maybe Mr. Mayer doesn't even know what's in them. I don't know. I'll worry about that later. All I'm concerned about now is my students doing the lab. Okay, so if everybody's got a different mixture, so don't try to rely on a friend like, what did you get? Did I get the same? It won't work. Okay, there's distinct mixtures for everybody. So what you're going to do is you're going to get an unknown. We're going to write the number on your fume hood of what unknown number you've got. And in that unknown, it's going to contain at least one of the, and this shouldn't say 3, that's a typo, of the 4 known analytes. Okay, so again, in your unknown, you're going to have at least a minimum of 1 of aspirin, acetaminophen, phenacetine, or caffeine. All right, then you're going to use the information from part 1 to decide what would be the best solvent or solvent system to run the TLC plate in. You're going to spot the unknown, right? Your unknown mixture, or maybe it's a single compound, and you're going to spot it against and again, there's another typo here, sorry, against the 4 known compounds. You're going to compare their RFs. Then you should be able to unequivocally state, I have, caffeine and I have phenacetine based off of these RFs. Now, notice that I asked you before that little quiz question where I said, if 2 compounds have the same RFs, are they identical? And you guys were all pretty smart. You all said, not necessarily, Mr. Dion. Maybe yeah, maybe no. Well, the way the experiment is set up is so that there will be no mystery compounds, okay? You will be able to unequivocally say, if this has got the same RF as acetaminophen, it's acetaminophen. If it's got the same RF as aspirin, acetylsilic acid, it's the same compound, okay? All right, because one thing we like you to do in your summary is we want you to unequivocally state, this is what is in my mixture. I don't want any, hey, it might be this, maybe that. I've been thinking about it. I've been scratching my head about it. No, you say, this is what it is, and this is how I know, okay? All right, so in the lab, follow procedures, collect all the data for parts 1 and part 2. You don't have, it says don't include the calculations in your procedures. Don't do that. Do those in the calculations. Put the calculations after. You have a bunch of calculations to do. I forget how many it is. I have it listed in here. So again, part 1, you do it in a trio, and I'm using quotation marks that you can't see because obviously due to social distancing, you're not going to be working next to somebody, but you're going to pool your data. And then in part two, you work by yourself, and there you go. All right, so here's what your TLC plates are. Again, I will probably just draw this on the board in my lab because, again, I like all my students to put everything in the exact same order. It just makes it so much easier when we go to the UV light and we look at everything. It just makes it easier to compare. Makes it easier to compare against your friends too. So there you go. Part 1, you write all the known analytes in your solvent. Again, we'll assign you a solvent, acetone, ethyl acetate, or hexanes. In part 2, you're going to run all the knowns and your unknown, and maybe let's say yours is number 9 or something. You'll write number 9, and then you're going to run it, and you're going to find out what components are in your unknown, and that's it. All right, that's the whole experiment. Post lab, make sure to calculate all the RFs for the 3 TLC plates. So let's do the math here. You have 3 plates total, 1 that you ran and 2 that your neighbors ran. and there's 4 compounds on each. So 3 times 4 gives you 12. So that's 12 calculations, 12 RF values you have to calculate for part 1. And then in part 2, you have the knowns. There's 4 of those, plus you have anywhere from what? What did it say? 1, there might be 1 to 4. So you might have anywhere from 5 to 8 calculations. Okay, so anywhere in that range for part 2, depending on how many components there are in your unknown. Show all calculations. They're very easy. You know, it doesn't take all night to divide 2 numbers, you know. Calculator. Significant figures count. Okay, you got to be able to read a ruler. So you should know the mantra of how to read a ruler correctly to the correct number of significant figures. You report the measurement to 1 digit past the smallest calibration. Since our rulers go to the millimeter, you're going to report to the 100th of a centimeter. There you go. And this is what the data sheet looks like. I'll show you in a second in more detail, but you're going to fill out the data sheet. I'll go over that in a second. And then make sure you keep everything clean. Make sure you wipe down your bench. Hopefully your instructor went over that with you, that we need to clean off our benches before we leave because, you know, somebody else is going to come in there. Let's see. Make sure you get your measurements from the TLC before you leave. If you lose a plate, you're in trouble. Then you've lost your data. Okay. You know, something I used to do in industry is I would take a piece of tape, like no kidding, Scott, and you're not going to do this, but I'd take a piece of Scotch tape, and when you touch it to the TLC, to the stationary phase, it'll actually pull off all of the data, you know, on the piece of Scotch tape, and you can tape it into a notebook. Again, we're not going to do that. It's easier to just draw it. There you go. And the sapling assignment for this one closes on February 20th. And I wanted to look at the data sheet, so just give me a second. Here are some hints. Now, Mr. Dion might have left a hint out here. You know, Ms. Herring, Mr. Mayer, you know, we're all good problem solvers when it comes to running TLC. So if there's something that I might have glossed over or just a detail that I've forgotten, forgive me. But here are some of the hints that I thought of while I was putting this together. Again, spot the analytes or solutes in the same order each time. That just makes it simple. Keep the spots small. Never double dip a capillary. You guys know the rule, you don't double dip a chip, you know, in the chip dip, right? It's disgusting. It's like sticking your mouth in the dip. Same thing with a capillary, okay? I don't know if I said that during the presentation, but you know those little capillary tubes I was talking about? Okay, those are single use. Okay, you use it once and then you throw it in the broken glass. Because think about it. If you put, you know, your first analyte in it and then it drains out, well, there's still going to be some residue in there, and then you put something else, then you're just contaminating everything. You're going to make a real mess. So just once the capillary is used, throw it away. What's next? Don't get the solutes too close to the edge, okay? The TLC plate is 5 by 10 centimeters. There's more than enough room to get everything on there. The problem is if you get your analytes, right, here's your baseline. If you spot it really close to the edge like that, oftentimes it will get kind of caught on the side, and it just gives you a spot that you will not be able to determine what the hell is going on, pardon my language. What else? Separate the spotting points evenly. So that means, you know, just kind of spread them out evenly across the line like that. Oh, here's a big one. And this is something I don't think I said today, is do not disturb the beaker during development. So your chamber, once you've put the TLC plate in and you've covered it with foil, don't touch it, okay? You only look at it with your eyeballs. Do not jostle it. Do not tap it. Do not move it around. You leave it. Hey, I have another question for you. Where should the developing chamber be while the TLC plate is being developed? Where should you have the TLC chamber? And it's not a trick question.
In the fume hood.
Oh, diggity darn. It's a good class. It's absolutely right. It's got to be in the fume hood. Don't do anything on the bench. Okay, we have fume hoods for a reason. I don't want to breathe in. I don't want to breathe in any solvent vapors. I don't want to breathe in acetone. I don't want to breathe in ethyl acetate, and I don't want to breathe in hexanes either. Nobody does. Okay, so do everything in the fume hood. Ideally, good RFs are going to be between 0.25 and 0.75. Now, this is something that I think I'm going to save to discuss with my students in the lab. So you could ask your lab instructor, if it's Miss Mayer, or Miss Herring or Mr. Mayer, about the whole concept of mixed solvents. I kind of figured I would run out of time today. So you can ask your instructor about this, and she or he could talk to you about mixing solvents. And if you're wondering, what does that mean? It means exactly what it sounds. You could take ethyl acetate and mix it with hexane. You can take acetone, you can mix it with methanol, right? You can mix all kinds of organic solvents. And the reason why you do that is it can really help you get resolution between or separate organic compounds, especially when they have the similar functional groups. You'll find that mixed solvent systems can come in really handy. So again, I'm going to ask the instructors to discuss that with you in the lab and just maybe kind of weigh up your options as a class, something to think about. What else? Don't let your fingers touch the TLC plate. Well, you should be wearing gloves the entire lab anyway. Mark the solvent line, the solvent front, as soon as you pull the TLC plate from the chamber. Never use a pen on the TLC plate. That's a big no-no. Just use a pencil and just touch it lightly. You don't have to press hard on the TLC plate. Otherwise, it'll just get mangled. And that's pretty much, everything I can think of that I need to tell you to get your procedure ready. So again, 2 parts. First part, you are going to run one of those solvents. Don't worry, your instructor will tell you which one to do. Miss Herring will say, I want you to run acetone. I want you to run ethyl acetate. I want you to run hexane. And then for the second part, Mr. Mayer or whoever your instructor is, me, I'm going to come up and say, hey, you're going to be unknown number 13. You're unknown number 2, whatever. So you're not going to be, wandering around in the lab guessing what to do. Okay. We'll have that all laid out for you. Now, what about waste? Okay, let's think about waste. There's something I did forget to say. Let's go back to the solvents. Where were they? I had them over here somewhere. Just give me 1 second. So we have 3 solvents: acetone, ethyl acetate, and hexanes. None of them are chlorinated solvents. However, you'll want to ask your instructor, I don't want to pour any of these solvents down the drain, right? None of these solvents belong down a sink. So make sure to ask your instructor where to dispose of these solvents properly. Okay, and there should be a waste container in a fume hood. And don't worry, that's something else. We'll never leave you guessing. We might ask you to solve some problems in the lab, but we'll never ask you to solve the mystery of what to do with waste. We'll tell you where that goes, okay? We don't want to pollute any more than we have to in organic chemistry. Well, let's take some time and look at the data sheet. This will just take a second. This is the data sheet that's available. Again, I posted it to Canvas in a .docx format. So if you want to just type on it in Word, be my guest. If you want to print it out and write on it neatly, be my guest too. So it says here in part A, you've got the 3 TLC plates. You've got the 3 solvents: hexane, ethyl acetate, and acetone. And again, you're going to get data. One of those solvents you're going to do yourself. The other 2 will be solvents that your neighbor or compadre did, whatever. Somebody else in the lab. You're going to write down solvent fronts. You're going to write down the distances traveled. You calculate the RFs for all of the knowns in each of the solvents. And, just based off of the data in the table, you'll be able to figure out, what the best course of action is probably. And then in part B, you're going to write down your number. Let's pretend it's number 33. I don't even know what the numbers are. Your solvent or solvent mixture, let's say you used, let's choose a solvent that's not even used in this lab. Let's say you chose dichloromethane and methanol. Again, it's not part of our lab. I'm just throwing it out there because I used to use this solvent system all the time in a program I worked on. So you're going to write down the solvent front. You're going to write down the RFs for all the standards, right? So you're going to fill in every single one of these boxes here. For these boxes, you're only going to fill in the ones that are of relevance to you. So if you only have component 1 and component 3, you're going to fill in those, and you leave the other ones blank. Just don't put anything in there. And then we want you to unequivocally, without question, state, come on, what the heck was in your sample. You're going to say there was 2 components in my sample, right? I had, phenacetine and caffeine or something like that. Okay. Now, next it says summarize the experiment. Don't misunderstand me. Summarize does not mean first I made a developing chamber, then I made a TLC plate, then I cut a piece of filter paper. No. The summary is what's shown here. So in about 3 paragraphs, we want you to discuss your observations in part A regarding the polarity of the organic molecules, the analytes, and the rate of the elution, right? You can say, well, in my reagent table, I predicted this one was the most polar. It's true because it had the lowest RF. I predicted this one was the least polar. I was right because this one had the highest RF, so on and so forth. Make sure you discuss your observations regarding the effects of solvent polarity. So discuss how the polarity of acetone, ethyl acetate, and hexanes affect the relative rates of elution. You can answer the question, did all the compounds behave as you expected them based off of your predictions in the table? And then in part B, you want to summarize what's your unknown ID number, what components were in there, what solvent system did you use, why did you select it, and how do you know that you unequivocally have those components in your unknown mixture? And that's it. Last, you want to put in some experimental errors. It says here, or puts in some errors, both experimental and technical. I'm not really all that concerned with technical errors a lot, but we want you to think of some actual errors besides I spilled it, I dropped it, I goofed it up, I stepped on a TLC plate or anything like that. Sorry, I've gone a little long today. Maybe I repeated myself a little bit during this lab lecture, but I want you to be aware of what you're going to do in the lab. And in the few minutes that we have left, are there any questions? I know that Mr. Mayer is in the chat, and he might have answered all the questions. Let's see.
Oh, I was gonna ask, will this recording be put into Canva or to your YouTube channel?
I'll post it in my YouTube channel. So remember to ring that bell and make me rich. I'm kidding. My videos aren't monetized. All right. Any other questions?
I just have a quick question. Are we allowed to take pictures of our TLC plates in case we want to refer to the data later, or is that not allowed?
Well, generally speaking, we don't like our students to bring their cell phones into the lab. So we have we have a no cell phone policy. So no, you don't need to take a picture. Just make a sketch of it. You can also, and Mr. Mayer might be able to provide some information on this, but you can keep your TLC with your unknown on it. We'll give you a Ziploc bag, I think, and then you can keep that with you. So if you want to keep it, yeah. So you could have that with you. Yeah.
Thank you.
And that's something that will give you more detail. Let me remind you of something. We'll give you a Ziploc bag for you to put your TLC plate in. And I don't know, are we going to run any other TLCs this semester? I'm trying to think. Yeah, I guess we will. You can recycle that Ziploc bag so we don't, there's already enough plastic in the ocean. Any other questions?
Oh, earlier you mentioned that we could either type it or print it out and bring it to class. So are we allowed to have computers out and type on that, or
Absolutely
did you mean
not.
afterwards?
Absolutely not. No, you're not bringing any laptops. You're totally misunderstanding me. Okay. The pre-lab is your header, your purpose, your reagent table, your safety table, your procedure. That is written with a pen. Let me show you. It looks like this, okay? A pen, and you're going to write, not green, but you're going to write that in black or blue ink in your lab notebook. I don't have a lab notebook here. Anyhow, you're going to write that out physically. The typing that's done, the only time you're going to type something is at home, okay? That's in the data sheet. Okay, for the data sheet, if you want to type in there, normally we don't fill the data sheets out in the lab. That's something that you'll do at home. Does that make sense?
Oh, yes. That's
okay.
What my question kind of was. If we were filling that in during class, but yeah.
Yeah. No. There's no need to have a laptop. The only reason I bring mine in is because I have to. Okay, no need for that. Yeah, I spent 15 years working as a bench chemist for a living, and it was the first 6 years that I worked. I only worked in paper. Wrote everything out by hand. And then after that, the second job I had, we had electronic notebooks. But it's a really valuable skill to learn how to keep a good notebook. You'll find that it's rewarding. If you keep a good notebook, the first time you write down an experiment and you do it well and you go back to it, you're going to thank yourself, okay? You're going to be kissing your own, so you'll be very happy with yourself. In fact, my supervisor in graduate school gave me and another graduate student such a big talk one time about how when he was doing his PhD, he didn't keep a good lab notebook. But more than that, what he didn't do was he didn't characterize all of the organic compounds he made along the way. Now, that doesn't mean a whole lot to you guys right now, but it will later. So what I mean is that he didn't run NMR and mass spec, and he didn't run all these different spectroscopic methods on all of his compounds. So he had to go back and remake compounds from like years before. He said it was just a total catastrophe. So anyhow, the better notebook that you keep, the more thorough that you are, it will save you so much time. Something, and this, I'm really preaching to the choir here, but something I think about when I teach general chemistry is if you think about general chemistry, how important units are. You guys all know that, moles, milligrams, grams, whatever. Units are so important in general chemistry. And I've seen this happen piles of times where a student will solve a problem, leave units out, even though the student understood what was going on, but made a mistake. So, details are never bad, You usually can't go overboard with the details in the lab notebook. All right, anyhow, I've gone overtime and I'm not supposed to do that. So I'm going to call it quits for now. Again, I'll post the recording to my YouTube channel. If you have any further questions, you can either email me or your lab instructors. If you go into our syllabus on Canvas, I have updated it so that I have Mr. Mayer's and Miss Herring's email if you want to contact them. And other than that, I'm going to see my section in the lab next week. I'm already looking forward to it. I enjoy doing experiments with my students. Also, in case you're wondering, you might think it's only 2 TLC plates and they only take 20 minutes to develop. You can finish this lab in under the allotted time. I'm not guaranteeing you can, but you can, especially if you're prepared. The more prepared you are, the faster you'll be able to do the lab. It's not a race, but you'll be able to work more. You'll be able to expedite the process, right? Work more efficaciously. Anyhow, have a good weekend, and I'll see you soon.